I'm Dr. Brad Stroud, Executive Producer of biotechproductions.com and veterinary specialist in the field of assisted reproductive technologies in cattle. Today, I would like to talk to you about artificial insemination and embryo transfer. After graduating from veterinary school at Texas A&M University in 1979, I did a one-year's internship at the Ohio State University. I took senior students on farm calls. It was the ambulatory division of the clinical practices there. After that, I came to Weatherford in the fall of 1980 and started Stroud Veterinary Embryo Services. Here we have specialized in reproduction with emphasis on embryo transfer. We've also done in vitro fertilization. We've helped pioneer ultrasound in reproduction in cattle and done gift procedures, gamete intrafallopian transfers for problem breeders. Along the way, I also became politically involved in the industry, and I've served as the president of the American Embryo Transfer Association and the International Embryo Transfer Society. Let's start with a brief history of artificial insemination and see where it's brought us to this point. Many people think of AI as a modern technology, but it has a long history. Apparently, artificial insemination was attempted on the wife of King Henry IV of Castile. In 1677, the Dutch scientist Anton von Leeuwenhoek saw spermatozoa through the newly invented microscope. More than 100 years later, in 1780, an Italian priest and physiologist named Lazzaro Spallanzani performed an experiment in his laboratory that revolutionized the way scientists thought. Until this point, scientists had a very primitive understanding of conception, largely based on how plants grew. They speculated that the embryo was the product of male seed nurtured in the soil of the female. Spallanzani's experiment on dogs proved for the first time there must be physical contact between the egg and sperm for an embryo to develop. With this new knowledge, Spallanzani experimented on frogs, fish, and other animals and was successful. Although Spallanzani's work paved the road for the future of artificial insemination, it was in the early 1950s at Cambridge University in England when a scientist named Chris Polge accidentally discovered how to freeze bull sperm. Basically, they had tried several attempts at freezing sperm and all the sperm died after thawing. But by accident, Dr. Polge put sperm with a chemical known as glycerol. And the glycerol actually helped protect the sperm during the freezing process. With Dr. Polge's accidental discovery of a good way, successful way to freeze bull semen, it opened the doors to a world of opportunity as far as commercializing the art of artificial insemination. We were then able to transfer the genetic components of animals from continent to continent, state to state, city to city, farm to farm. What this meant was that a bull of extreme value could then, instead of breeding 10 or 20 cows per year, could then be collected, have semen collected, frozen, and shipped literally anywhere in the world. Obviously, this has huge implications commercially and for the concentration of the most valuable genetics in the world for beef and dairy cattle. Cattle breeders can purchase frozen semen either from bull studs or from individual bull owners. Bull studs are typically where bulls are taken for the semen collection process, where it is mixed with semen extenders and chemicals to help protect it during the freezing process. The freezing process is done in cool rooms. The sperm is essentially mixed with the chemicals, allowed to cool over several hours. Then the sperm is evaluated for motility, and if healthy, the sperm are then frozen in special freezing compartments designed for freezing semen. Once the freezing process has occurred, those units of semen are then stored in very large liquid nitrogen vats at the temperature of minus 190 degrees Celsius, about minus 321 degrees Fahrenheit. There, sperm can be stored indefinitely without damage. Now, normally, when a bull ejaculates, he produces several billion motile sperm. So if he breeds a cow naturally, then only one of those several billion sperm are going to fertilize the egg that she's ovulated. But with artificial insemination, the power of AI is such that that bull's ejaculate, that several billion sperm, can be extended into several hundred straws. One straw typically contains anywhere from 10 to 30 million motile sperm. Thus, from one super herd sire bull could be used to inseminate hundreds of cows. Thus, the power of artificial insemination. During the breeding season, ranchers watch for their cows to come into estrus on a daily basis. Usually, estrus is detected early in the morning, at noon, and again late in the afternoon. Once a cow is found to be in estrus, approximately 12 hours later, she is put in a breeding chute to be artificially inseminated. At that point, a straw of semen is put in a warm water bath, about 95 degrees Fahrenheit, for about 30 to 60 seconds. At that point, the straw is then removed from the water bath, wiped dry with a clean towel, and then placed in the artificial insemination instrument. The artificial inseminator then takes the loaded gun to the cow. Here, the gun is inserted into the reproductive tract of the female, and the gun is manipulated through the cervix, where the tip of the gun is then located in the body of the uterus. At that time, the insemination gun then expels the frozen semen into the uterine body cavity of the female. Here, the several million sperm will reside, but eventually most of those sperm will come back retrograde out of the cervix, back into the vaginal cavity. However, there will be several million sperm that do make it down through the uterine horns, and where a limited number finally will make it into the fallopian tube. Usually only several hundred sperm make it all the way to the fallopian tubes where fertilization occurs. That's only several hundred sperm out of 10 to 30 million motile sperm that were actually inseminated into the cow. One of the biggest advantages of artificial insemination is that cows' estrus periods can be synchronized together. Large groups of cows can be synchronized with their estrus periods all coming over a 2 to 3 day period. This means that the artificial insemination is done during a couple of days, and 9.5 months later, during the calving period, they're all calved at one time. This saves a lot of labor and concentrates your labor over a short period of time, but most importantly, creates a very tight, uniform group of calves at weaning time or marketing time. This is very beneficial to both buyer and seller. From the 17th century until now, there have been great strides in the science of artificial insemination using frozen semen. Herds now can be, by the hundreds or even thousands of cows, can be synchronized over a short period of time, inseminated with genetics from the greatest beef and dairy bulls in the world. Thank you, Mr. Spallanzini. The advantages of artificial insemination don't stop with the normal single ovulating cow. AI can be used with the technology called embryo transfer. In embryo transfer, very super valuable females are super ovulated and allowed to have multiple eggs per ovulation. Then the frozen semen is thawed and used during the estrus period during this superovulation to fertilize her ovulating eggs. So the two technologies essentially go hand in hand. Embryo transfer in cattle has recently gained considerable popularity with seed stock, dairy, and beef producers. Most of the applicable embryo transfer technology was developed in the 1970s and 1980s. However, the history of the concept goes much further back. Embryo transfer was first performed and recorded by Walter Heap in 1890. Yes, he transferred 2 Angora rabbit embryos into a gestating Belgian doe. She went on to produce a mixed litter of Belgian and Angora bunnies. Embryo transfer in food animals began in the 1930s with sheep and goats, but it was not until the 1950s that successful embryo transfers were reported in cattle and pigs by Jim Rowson at Cambridge, England. The first commercial embryo transfers in this country were done in the early 1970s. Initially, embryos were recovered from valuable donors and transferred to recipient animals using surgical procedures. It was not until non-surgical methods were developed in the early 1980s that embryo transfer exploded in its popularity. So, with embryo transfer, essentially gonadotropin from the pituitary of sows and boars are injected twice daily for 4 days into the cow. And the target organ for these pituitary extracts, or follicle stimulating hormone, is the ovaries. It's what makes a sow have a litter of pigs. The amount of follicle stimulating hormone circulating normally in a sow makes the ovaries, the target organ, grow multiple eggs. Therefore, the sow ovulates 10, 12, 15 eggs. The boar breeds the sow, or artificial insemination fertilizes those eggs, and ultimately a litter of pigs result. Well, the same thing happens with a cow, except we don't let the embryos stay in the uterus and go to term. In the cow, the uterus is only meant for one fetus, maybe 2. They're fertilized with either frozen thawed semen or semen from a natural mating by a bull, and the cow develops one embryo all the way to term. But with embryo transfer, again, the follicle stimulating hormone is injected from a sow. It's a preparation from a sow's pituitary, is injected twice daily into the cow for 4 days. At the end of that 4 days, the cow's ovaries have responded just as if she were a sow. They ovulate multiple eggs. At that time, frozen semen is thawed and artificially inseminated into the uterus, where the sperm makes its way to the fallopian tube, fertilizes the multiple eggs, turning them into embryos. But the embryos, remember, in the cow, there's not enough placental area for the placenta from multiple embryos to attach to the uterus. It's a different type of placentation. So what happens is that we have to wash or flush the embryos out 7 days after the fertilization process, or the artificial insemination. The embryos at that time are encased in an eggshell called a zona pellucida. The embryo is literally free-floating in the uterine fluids and is easily accessible through non-surgical flushing techniques. The solution that goes through the cow to flush the uterus is run through a filter. The filter is 50 micron mesh. The embryos, being about 120 to 150 microns in diameter, don't go through the filter. The filter is rinsed into either a round or square searching dish, and there the technicians find the embryos and place them in a smaller holding dish. The embryos are then graded and either loaded into straws and transferred fresh into recipient cows, or the embryos are prepared for freezing. The freezing process is about an hour and a half long and is very similar to freezing sperm. The embryos have to be dehydrated so that intracellular water molecules are not frozen, which creates crystals and creates tissue damage. Instead, they are dehydrated with certain chemicals that dehydrate the embryo. They are then frozen and stored in liquid nitrogen to be preserved for any number of days, months, or even years, or even decades. But let's talk about the recipient cow. You can't just get any old cow out of the pasture at any time of the month and drop the embryo in her. If you do, death is imminent for that embryo. A recipient must be prepared. The reproductive tract of that cow has to be in synchrony with the growth of the embryo. Let me describe that. Normally, when a cow has an estrus period, her normal hormone profile is high in estrogen and low in progesterone. Okay, and when fertilization occurs, or immediately after fertilization, progesterone begins to build up, but slowly over a 2, 3, 4 day period. And every day of that reproductive cycle, the normal hormone profile of that cow changes. The uterine lining of that cow also changes as the embryo progresses. So ultimately, what I'm trying to say here is that we flush embryos 7 days after the cow's estrus period. The embryos are about 100 cells at that stage and encased in a clear eggshell called a zona pellucida. Now, the embryo is recovered 7 days after the estrus period. It must go back into a recipient cow that was in estrus 7 days ago. In other words, the reproductive tracts of both the donor and the recipient female must be in hormonal synchrony. That way, the embryo is being removed from a uterine environment and placed back into a very similar uterine hormonal environment. Otherwise, conception is not likely to occur. The success rate of transferred fresh embryos into recipient cows is usually in the 60 to 70 percentile range. In other words, if we collect 10 embryos from a donor and we transfer all of those fresh, we can normally expect 6 to 7 of those to result in pregnant surrogate cows that will deliver a healthy live calf. Normally, taking statistics from the American Embryo Transfer Association, the average donor female in a flush, at least beef cow, produces almost 7 viable embryos. Conversely, on the other hand, dairy cows produce about 5.5 embryos on the average after being superovulated and flushed. Embryo transferred donor females are typically flushed on a year-round basis. However, embryos recovered from those cows are usually only transferred during the milder fall months or the milder spring months. That way, the calves born are not born during the harsh cold winters or the very difficult and hot summertime. The scope of the embryo transfer industry can be best explained by dividing it into beef and dairy. Essentially, there's about twice as much beef embryo transfer done as there is dairy. Let's take a look at dairy cattle first. In the year 2006, the American Embryo Transfer Association reported 17,000 dairy donors being flushed. That produced 90,000 viable embryos, of which 52,000 were frozen, 38,000 were transferred fresh. Now, conversely, if we look at the beef embryo transfer side of things, in the United States in 2006, 35,000 beef donors were flushed, producing 230,000 viable embryos. 62,000 of those were transferred fresh, 155,000 were frozen, for transfer at a later date. Looking at the international statistics, the United States does about 39% of the world's embryo transfer data. For example, in the year 2005, there were 131,000 beef and dairy cows flushed worldwide, producing about 612,000 total embryos. The advantages of embryo transfer technology are obvious. For example, a non-superovulated beef female will have 7 calves in her lifetime. She'll calve as a 2-year-old and have a calf every year until she's about 9, for a total of 7 calves. If you take that same cow, however, and superovulate her and flush embryos from her, let's just say we do 10 flushes over her lifetime, which could easily be done. If she produces 7 embryos each flush, that's a total of 70 embryos. So if that produces 35 live healthy calves, then compare 35 to 7. And let's look at the female-male ratio. For example, if a natural ovulating cow has 7 calves, 4 of those are likely to be males and 3 females. So the average beef female will have 3 heifer calves in her lifetime. With embryo transfer and superovulation, however, that same cow will have 35 calves, or will produce 35 calves using surrogate females, 18 of which would be males, and let's say 17 females. So compare. A non-superovulated cow, traditional breeding, will have 3 heifers in her lifetime, whereas a cow with 10 flush procedures done will have, 15 to 17 females in her lifetime. So I think the numbers speak for themselves. Artificial insemination and embryo transfer have certainly paved the way for future reproductive biotechnology.